Okay, so we're just going to do a quick recap about projections because it's one of those, slightly less obvious, that's not what I just said, less intuitive kind of examples or of dot product. And so the idea of what a projection is, so big picture, you have two vectors attached at the tail, and you want to project one onto the other. So think of, we want to drop a perpendicular from the head of one to the direction of the other. It might not actually attach to the other vector, but on the same line as the other vector. And whatever that vector's magnitude and direction are, that's the vector projection. Okay? And we talk about the fact that if the angle is less than 90, okay, then the vector will go in the same direction as the second vector. And if the angle is bigger than 90 but less than 180, so obtuse, it will go in the opposite direction. And if it was 90 degrees, the answer, it would actually have 0, because it would, think of it like this picture, think of it like a shadow of something that's perfectly vertical that has no shadow, okay? Whereas as soon as you have an angle, now there's going to be a shadow. Is this making sense, everybody? Okay? So, moral of story, like after we did all this work, and I wanted to try and show you the way the scenario works, this is your formula that will tell you the length of any projection. You take the vector you want to project, multiply it by cos angle between vectors, you get the length of the vector projection, finito. If you want the answer to be as a vector, okay, then this answer right here, this is the formula you use that will give you the vector projection, because the answer this time is not a scalar, it's a vector. Okay? It's built by taking the magnitude of the projection and multiplying it by a unit vector. So we've talked about unit vectors. A unit vector is a vector that is 1 unit long and goes in the same direction as a certain vector. Okay? So this is what that is right there. If you work with dot product, though, we can create this version of the formula that's a little bit easier, because then you don't have to necessarily have a picture to be able to answer this. Okay? Because it's just a plug and chug into a formula. But I wanted to go through what the formula means. That's why we did the scenario. And again, we went through it in a lot more detail in the previous video if you want to get a little bit more clarity on what a vector projection is. So we did the geometric examples, and we were just about to do the algebraic, or we just finished the algebraic one. So if I want the projection of vector 2, negative 3 onto vector C1, 4, okay, we used the formula. So again, the formula for the vector projection, majority of the vectors in the formula are what you're projecting onto. And then it's dot product over magnitude of vector C squared times vector C. So this was the calculation we did. We were so excited that we did it at the end of the period yesterday, or on Friday. So this is the way I would see on a test or on an assignment, like an assignment next week, for example. This is totally what I would do. I would do a dot product calculation at the side, I do a magnitude calculation at the side, and then just plug those values in and get my answer. Okay? So for D, it says illustrate the projections in parts A to D geometrically, or A to C geometrically. Let's not do that part. I think we got the hang of it, unless you really want to see it. So like, we kind of already did A and B. Like, you guys get the red vectors in both A and B are the projections. Okay. If I wanted to do this one, maybe I'll do it. So in C, okay, I draw those two vectors. So let's draw the picture that goes along with this, just so we can all see it. So if I say we have to draw the vector 2, negative 3, and the vector 1, 4. So I'm going to do something here just to kind of solidify it, anchor it all for ourselves so we know what we're doing. Okay. Are we all feeling comfortable that we could draw vector D, which is 2, negative 3? Start where? Where should I start my vector? At the origin. Go 2 units. So here's the tail of my vector. It's going to go 2 units to the and 3 units. Okay, so there's the head of my vector. So I have just drawn a geometric representation of vector D. Okay, now I'm going to draw vector C. So vector C is 1, 4. Okay, so I would draw 1 unit right, 4 units up. So there's vector C. Okay. So I want to draw the scale, the projection of vector D onto vector C. So at this point, I'm going to get everything I need now is in the picture. So let's zoom in on the picture itself. Okay. So we're normally used to everything kind of being related to the horizontal, but you guys get that we want to project green vector onto red vector. And if you remember, the rule is it's dropping that perpendicular. Drop it like it's hot, right? We want to drop a perpendicular to vector C. But wait a second, is there any way that I can go from the head of vector D to the current vector C and get a right angle? Is there any angle over there that's going to be a right angle here? Doesn't look, they look pretty much, they look like acute, like there's not. Where would you want to drop it? Where would the perpendicular be? Heading more into quadrant 3, wouldn't it? Like, what I'm saying is, okay, maybe I'll talk about this. Look at the angle between C and D right now. How would you classify it in terms of acute, right, or obtuse? So remember what we said, if the angle's obtuse, your projection's going to go in the other direction. Or for now, what you can just do is kind of extend the direction line of C, so you have someplace to aim your perpendicular.
And then that to right.
Can I now visualize from green to the red dotted line a right angle?
Yeah.
So if I drop, like again, I'm using the word drop perpendicular very loosely here, but I'm dropping it to form a right angle. Like this is the key, right? I'm forming a right angle. I have
to go that way, or could you have like connected it to the bottom?
Then it wouldn't be right. Like that's not a right angle.
No, like over there, another corner. Is that eight or
no?
Like where the G is. Like that.
Well, I want to. It's D on to C.
First an interruption, Ms. Bridgeford. Could we see Mara constant guidance, please?
Sure. Okay. So right now, by dropping this perpendicular, do you guys get? I'm now basically creating the shadow or the projection of D onto C. So this little purple vector here, do you guys get that's the vector projection of D onto C? And then I want you to kind of think about, it's not perfect, but negative 10/17 and negative 40/17. Does that vector, that purple vector, kind of look pretty close to what that is? Like maybe a little off, but again, I don't have a grid scale here. But if I said I went, a little less than 1 unit left and a little more than 2 units down, like you guys get like that purple vector seems to match what the algebraic vector or the Cartesian vector here is. So the purple vector here matches this algebraic vector here. So that's the key. So that's visually what you found. Okay? Does that make sense? Okay. So if you follow the purple vector and you went negative 10/17 left and negative 40/17 down, you should end up pretty much where the head of this geometric representation is, which is a good clue that you did everything correctly. Okay. So, okay, this example is so contrived. We're still going to do it, but it's in the homework. But you guys are going to laugh at it. So it's like, why would you even answer this question this way? But it is like a shoe store sold 350 pairs of Excalibur shoes and 275 pairs of Camelot shoes in a year. Excalibur shoes sell for $175 and Camelot shoes sell for $250. Write a Cartesian vector S to represent the pairs of shoes sold. So we're going to do the shoe vector. So create a Cartesian vector. So they want you to create a vector that has an x coordinate and a y coordinate. So what are we going to, like in the context of this problem, what are we going to say the x coordinate represents and the y coordinate represents?
shoe store sold 350 pairs of Excalibur shoes and 275 pairs of Camelot shoes. So I have two pieces of information about shoes. So there's going to be a price vector, and there's going to be a shoe vector, okay? And so for the shoe vector, what do you think should go into the x coordinate and y coordinate? What are the two pieces of information you have about shoes here?
The amount and price.
Just don't care about the price right now. I have the amount of how many different pairs of shoes. 2 pairs? 2 different types of shoes? 2 types of shoes? I should say types. 2 types of shoes? Bingo, yeah. So what are we making a decision? We're making a decision. By creating this vector, we've made a decision. First coordinate represents anything to do with Excalibur, and second coordinate or y coordinate represents anything to do with Camelot. Because we've got to be consistent, because we can't, when we do the next vector, we have to keep the same order. Okay? So when I do the price vector, I need to keep, and it's going to be price of Excalibur, comma, price of Camelot. Price of Excalibur is, these are fancy shoes, $175. And price of Camelot shoes, $250. Okay. So you've just done an algebraic representation, okay, algebraic representation of the data in this problem. If you find the dot product, you might be going, okay, what's the purpose of this? If you find the dot product, does it end up telling you something kind of interesting? So if I do the dot product, so let's see if we remember how this works, guys. Remember the rule for dot product, algebraic dot product? First times first plus second times second, right? A1, B1 plus A2, B2. So if I do first times first plus second times second, first times first plus second times second. I'm going to hold off calculating for a moment. Can you see what calculation has just been created here? Just think the big picture about the shoes. Like what calculation has just been formed? Pardon?
The total amount of money that's like for each.
You're going to get the total amount you make on these shoes, right? Because you're going to get how much, like the total amount generated from those, the 350 pairs of Excalibur shoes, and the total amount generated from the 275 pairs of the Camelot shoes, because you're multiplying by the dollar amounts. So if we do this, I'm going to do it in pieces again, just to kind of see the visual of how everything gets calculated. So if I do 350 times 175, 61,250. 275 times 250 is 68,750. And if you add those two dollar amounts together, you get 130,000. What does the dot product represent? The dot product represents the total dollar amount maybe total value of the shoes, maybe? Is that better? Total value of the shoes. Okay, 130,000. So this is the reason why I preambled before we did this question. Like, first of all, was that like the easiest question you could think of? I mean, when you look back at it, grade 2 vectors, dot product done. If you were in grade 9, you had no idea what vectors were. But I said, how much money will you cost? Maybe not in grade 9, grade 6. How much money will it cost? Will you get if you sell all the shoes? Is that literally the calculation? The right side of that equation, or the dot product is what you would do, right? Okay, take the dollar amount times the number of shoes plus dollar amount times the number of shoes. You would get this dollar amount. But it is useful to recognize that. Do you guys get that this is how like computers organize information? So you're basically turning the information into sets that can be used in the background in the computer. Like that's, I don't know how many of you are, any of you on computer science, or any of you thinking that computers or programming might be in your future? Because in the sense of when you're working with computers, sorry Jane, I marked you up. I just realized, sorry, you might have just run down, okay, sorry. So, what do you think? In the background of a computer, okay, it has to store things in like a sets. So you program it like, I'm going to store all these in something called an array, for example. The arrays are kind of like vectors. They're just like a whole bunch of data separated by commas. And so if you have all these things organized and you say, I want my total profit, then you guys see it's just playing around with these structures. And that's what we're kind of doing there. We're saying, I'm taking something that normally would just be a calculation and turning it into a more formal structure that can be manipulated in the context of larger amounts of information. Because how many shoe stores have two types of shoes, guys? If you only had two types of shoes at your store, you're probably not going to be the most popular shoe store, right? So when you go, like, ballpark, how many shoes do you think, a store, different types of shoes would a store have? Okay, that's a very technical number. 1,000, 10,000?
Oh, for like
Different types of shoes.
in a warehouse?
Or like Browns.
Brown?
Yeah, if you go to a Brown store, how many different types of shoes? Couple thousand? 2,000? Can you, because this is going into something there's just something to think, the big picture here. We've just created vectors. We're actually going to touch on this right away. These are vectors that are two-dimensional. Okay? We're about to start talking about vectors in 3 dimensions. But could you create a vector that has 2,000 entries?
If you wanted to, yeah.
And could it be, you organize all 2,000 numbers of shoes in your warehouse here, and then you put all the prices of every shoe here. If you did like a massive dot product, would that be the total value of all the shoes in your store?
Yes.
And do you guys get, if you can store that in a computer, a 2,000 long vector and a 2,000 vector, and say, hey computer, can you dot product that for me? Is that going to be a lot faster than you going, okay, first number times first number plus second number 2,000 times? Right? Like, that's the purpose of this. You can, if you set up in a structure that's easy to do, and now, hey computer, do this. See, that's what the calculator is doing in the background. It's doing that calculation. Okay, that's how spreadsheets work. In the background, like, you see what you see, but in the background, this is what your computer, all these pieces of data are just stored in all these little places in your computer, and it has to figure out what to do with it. It's doing these types of calculations in the background. Anyway, that was a bit of like a tangent, pun intended. Okay, but I just want you to understand that there is some usefulness to this, but I think it's a little bit of a contrived question. But maybe it will be nice to put one on your assignment. It's like easy. Okay.
Yes, bless us.
Bless you. Okay. So let's see how blessed we are when we look at 7.4. So now we're going to deal with 3 dimensions. Okay. Who's a good 3D perspective drawer?
No.
Any rap artists?
Mara.
Okay. So I'm gonna try and make life as easy as possible to do this, but I want you to understand that we live in a 3-dimensional world, and so we have to sometimes deal with 3-dimensional vectors. Okay? And so that's what the purpose of today is. We're going to take everything we've learned, and the nice thing is, you kind of need to represent 3 dimensions. You kind of need Cartesian vectors to do this, because in 2 dimensions, how do you other than drawing a 3D perspective drawing and trying to draw vectors in 3 space, it's actually easier if you have a coordinate system to work with as opposed to just, I'm drawing in space. Okay? So we're going to extend our knowledge of vectors into 3 dimensions. We're going to use a Cartesian system to represent 3D points and vectors. So we're going to spend a good chunk of today's lesson talking about how we represent points and therefore vectors in 3 dimensions. So throughout high school, we've been using the Cartesian plane to represent the graphs of relations. A plane is 2-dimensional, allowing us to plot points of the form x, y. In order to graph in 3 dimensions, we need to introduce a third axis, and we call the z-axis. You ever wondered why we started with x and y? Why don't we just go y, z? Because z was being saved for this one moment, okay, to shine. So the z-axis is the 3rd dimension, okay? And so the way we represent this visually is think of the x-axis coming out of the page. So this is in perspective drawing scenario. Really what's happening is This x-axis is really doing this. For those of you watching the video, I've literally put a smartboard marker coming straight perpendicularly out of the board. Okay? That's really what the x-axis is doing. But unless you guys want to have like a pop-up assignment, pop-up exam, where like vectors are popping out of it, take your pipe cleaner and no. But that's the representation of what x is. So we put it on this angle, but we're understanding that that's really coming over like out of the paper. Okay, and so and then we have a positive y-axis and positive z-axis. We always draw those like horizontal and vertical. So you might be saying, well, why doesn't Z get the one coming out? But this is just the way we think of things. We want to still think of X and Y being our default, and almost think of it like you put the XY plane on the floor, okay, and then the Z axis comes out of the floor, and now you've added a third dimension, okay? And so right now, just to lessen confusion, I've just drawn the positive x-axis, the positive y-axis, and the positive z-axis.
It's negative.
Yeah, so
Wait, how would the X one go in? Like,
yeah, so like into the board, right, would be the negative x-axis. To the left would be the negative y-axis, and down would be the negative z-axis.
it's just upside down.
Yeah, it's you just extend, but I want you to, can you kind of see the 3D-ness of this, okay? And so the idea is that we lessen the confusion by not drawing those extra axes. Like we don't draw it full all the time. We kind of stick with the positive axes, and we only really use the negative when necessary. Okay? So we call this a right-handed system. Okay? And so we're gonna do a little stretching with me. So we're gonna take our right hands. Okay? You place your hand in front of you with your thumb pointing up. Yay, look at us. Yay, okay. So, if the thumb is your thumb, okay, is the z-axis, okay? Now, point your index finger straight out to the left, okay? This represents the x-axis, and then make your remaining fingers point towards your chest, and that's the y-axis. So you have x, y, z. Does this make sense? X-axis pointing to the left, y-axis pointing towards you, z-axis up. So that's your default order. So x, y, z. Okay? Okay. X-axis, but from your perspective, it's, yeah, like a y-axis is pointing towards you, z up. Like it's to make sure everything's going in the right order. X, and then like y is in this direction. You don't even have to know this really. It's a
I read on the
convention.
text and you like.
Trust me, there's something that you have to actually consider going. When we get to cross product, there's actually a usefulness for doing this. We'll talk about it when we get there. Okay. So anyway, okay. So the other thing is, it says on your paper. I think I forgot to put it. So. On the paper it says that, so hopefully you kind of recognize that, I'm missing a slide maybe. Okay, so we plot points, okay. So I'm going to have to add a slide here just to kind of match up to your notes. So, okay, so in your notes guys, it says, we plot points in 3D, just like we do in 2 dimensions. However, we need to create a rectangular prism when we plot so you can visually see where the point is in space. So let's plot the point 2, negative 3, 7. So I'm going to draw this out here. My apologies, I don't have a slide for this, but so this is already on your paper, okay, your X, Y, Z. So the one thing you're going to notice is we're not going to really be doing scales a lot here, but we have to still try to keep things in proportion. So if I want to plot the point 2, negative 3, 7. Well, if I said we're plotting a point, where do we always start counting when we plot points? We start at the origin. So we're still going to start at the origin. Now, what I'd like you to do is, I want you to kind of leave a trail as you plot this point. So what I mean by that is, I'm about to go 2 units in the x direction. So I want you to make a call and say, like, this little dash length, you're going to decide that is a 1 unit. You're going to make that your default 1 unit. You decide how big you want to make it, but just be consistent on your paper. Okay? So you guys see I counted out 2 dashes, and I'm going to put, I'm not going to put a dot here because I'm not done, but I'm leaving a trail. I went 2 units in the x direction. Okay? Now I need to go 3 units, but it has to be negative in the y direction. So what the y-axis is going over here. So what does a -3 indicate? Go in the opposite direction of the positive y-axis. So I'm going to go 3 dashes. 1, 2, 3 in the y direction. And now to finish off, I need to go in the z direction. 7 dashes. 1, 2, 3, 4, 5. Okay. Ta-da! That's the point 2, -3, 7.
So 2 is x,
Yep.
y,
Yep, x, y, z. So, now, first of all, if I don't leave a path, do you guys get this point? I have no reference of what you did. If without a path, I'm like, yeah, I put it there. I'm like, how did you get there? But even this isn't that great. It's hard to still see the 3 dimensions. So what I'm going to do is, we're going to finish the box. So do you guys get, you've kind of done a length, width, and height of a box, but you've only done like one edge of each. Could we kind of fill in the blanks and make it a full rectangular prism? And you guys watch this because you're going to have to do this. Okay. Let's complete the bottom of the box. So everything should be, it's a rectangular prism, so everything should be perfectly the same size. Okay. So if I go 3 over here, if I start here and I go 3 units over, so that this length and this length should be the same, and then 2 units down. Do you guys see I just did the bottom of my box? And now I'm going to do all of the verticals, because you guys see I now have 4 points at the bottom of my box. Okay, I can now go 7 units up from every one of those to get the heights of every part of my box. So at the front, do you guys get this front one should mirror image this exactly. So it should be like 1, 2, 3, 4, 5, 6, 7. So this should line up perfectly with that front, because it's like the front of my box.
Why is that?
Because it's like it went the same amount forward. I just didn't go to the left. But if I'm creating the space in which this point, if you think of the rectangular prism or the 3 dimensions this point lives in reference to the origin, I would need to go 2. I want to kind of see the space. So the front of the box here should be the same height as the front of the box there.
But why are we thinking of it as like a triangle? Because that's what I'm seeing.
If I finish this, you'll maybe it'll be help. Okay. I'm going to close up the top. 1, 2, 3, front of box. Now I'm going to do the back of the box. Okay? So I'm going to start here. Do you guys get that I have to end up going higher than this? Let's start a little bit higher, right? So it's going to be 1, 2, 3, 4, 5, 6, 7. Okay, it should be right on the z-axis, but my z-axis is a little bit wonky. Okay? And then I'm going to have 1, 2. 1, 2, 1, 2, 3. Do you guys kind of see in 3 space? I've created a rectangular prism. There's one more up. 1, 2, 3, 4, 5, 6, 7. So this point is 2 units in the positive x direction, 3 units in the y direction, in the negative, and 7 units up. There's that point in space. And the reason I want you to get used to doing this is eventually that point might be the end point of a vector. And if I don't draw this yet, because we're not doing vectors yet, but if I draw the vector that starts here and goes to there, do you see how it's in a box? It's in 3 dimensions. Without the box, right, it's going to be hard to visualize what's that red vector really doing. I'm just going to, let me get a box just to illustrate this. So don't draw the vector here, that's extra info at this moment. But. Okay, for those of you watching the video, I just took like a photocopy paper box. Okay, so here's a box, guys. Okay. So visually what just happened is, if this corner, the back corner of the box, okay, if this is the origin, do you guys get that the point 2, -3,7 is out here? That's it, where my finger's touching over here. So it had to go in the X direction, in the Y direction, in the Z direction. So it literally, it's gone through space. It's not just been on a flat surface, it's in space. And if I draw a vector, it's like me putting a string in this corner of the box and pulling the string over to this corner of the box. It's in 3 dimensions. Okay? So it would be coming through the box. So that's why we use rectangular prism to represent this, to really get the 3D vision of what's happening. Okay? So again, the vector shouldn't be drawn here. All you had to draw was the coordinate, because that was plot the point 2, -3,7. That's what we did. Okay? And then it says a 2D graph has 4 quadrants. A 3D graph has 8 octants. Does that make sense? I'm going to go back to this picture here. How many places could you draw a box? You have, like, think of it like you could go forward to the right and draw and go up for a box, forward to the right and go down for a box. Forward to the right, forward to the left, go up for a box, forward to the left, go down for a box. And you can do all of that backwards. Backwards to the right, down, backwards to the right, up, backwards to the left, down, backwards to the left, up. So there's 8 octants. Okay? There's only 4 quadrants, right? But because as soon as you add an extra dimension, you can go up or down. Now you've doubled it. So now there's 8 octants. I'm going to make life really easy for you, though, guys. We're going to use just some generic, we're going to use front, back, left, right, and top, bottom as like our words to describe each octant. So it's not like we have the Roman numeral 1, 2, 3, 4 that we typically do for quadrants. We're just going to use a 3-letter acronym. And you always go front, back first, front, back, then left, right, then right, left, then up, down. So the first example here, describe the octant in which each point is located. So 1, 2, 3. So do you read that all 3 of those coordinates are positive, so you default to the positives. So out of front and back, the positive there is front. Okay. And then left, right or left, you're going to default to right. And 3 up, down, you're going to default to, or top, bottom, you're going to go T, right? So our defaults are front slash back, right slash left, top slash bottom. The ones before the slash are the positives, the ones after the slash are the negatives. Okay? So -3, 2, 1. So what would change there? So -3, you would go. Yeah. So you go negative, positive, positive, back, right, top. The first one was positive, 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 front, right, top. What's going to happen to -3, -2, -1? Back, left, bottom. And 1, 2, -3. Front, right, left. That's all I would want you to write. 3. If you want it, you could write the full words out if it helps you, if you're not sure. But that's what that would be.
Can we put something like that?
Yeah, sure.
Thanks.
Okay. It might be part and parcel of like, draw this vector or draw this point and what octant is it in? You know, it'll be like part of it. It's not gonna be, not a whole page of these, sorry. Okay. All right. So now, let's try and give this a whirl here. Okay. Plot the points A, B, C, and D, and describe the location of each point. So we're gonna basically do what Brianna said. We're gonna draw the point, and then we're gonna state where it is. So 2, 6, 1. So okay, get out your little pencils here. We're gonna do our dashes. Make a path. I sometimes use this reference, but no one knows what I'm talking about. Has anyone heard of like the comic strip Family Circus? It's like it's about this family, and there's 4 kids, and they like, and sometimes like it's Billy and PJ.
And it's usually like in a circle kind of
Yeah,
thing.
and it's in like the comics. Like if you go to like if you ever get parents get the newspaper, it's called Family Circus. Anyway, there's like sometimes you'll see like Billy was supposed to go right home, and it like follows him like going everywhere except home. Like he goes to pets this dog, and he goes down the slide. Like, and there's like literally this dotted line following him. And so this is kind of the analogy here, but no one knows what I'm talking about when I say that, so I try every year, and like maybe you might know. So anyway, this is kind of the idea. You have to make a pathway, make your dotted line pathway to plot a point. So 2, 6, 1. So I start at the origin, and I need to go, and keep in mind that you're going to eventually have to get 6, so don't make your dashes too big, or else you're going to, because you want to keep all your dashes the same size. Do your best. So 2, so I'm going to go 1, 2 units in the positive direction. And then 6 units, so which way should I be going 6, to the right or left? Right? So 1, 2, 3, 4, 5, 6. And then I need to go 1 unit up. So for me, my dashes ended right around where the y-axis label is. Yep. The only one that's on an angle is the x-axis. Everything else should be horizontal and vertical. Okay. Okay, so right now you have plotted point A. There it is. So let's fill in the rest of the box to make it more visual in 3 dimensions. So let's go 6 units back here. So 1, 2, 3, 4, 5, 6. And the point here should be that if you did this correctly, when you draw the 2 dashes going this way, that it should be parallel. Does that make sense, guys? Like it should be creating parallelograms on the top and bottom, and rectangles everywhere else. Okay, well, parallelograms here and here, rectangles front and back, parallelogram sides. So for the most part, I think I'm good. So there's my 2 dashes going on the diagonal there. So there's the bottom of my box. Okay? How far up from every corner, how far up does my box go from every corner? 1 unit. So 1 unit up, 1 unit up, 1 unit up. And then once you have that template done, everything else is just like copy the bottom on the top. Okay, so 6 across, 1, 2, 3, 4, 5, 6. Okay, 2 towards the back, 1, 2, 2 towards the back, 1, 2, and then 1, 2, 3, 4, 5, 6. Do you get the better perspective of the 3D scenario here? Can you see A in space now because the box is there? That's the purpose. Okay? Now, Desmos actually has, Mr. Spadafora showed me, a 3D grapher option. Okay? Maybe tomorrow I'll show you it. It's useful, but it doesn't complete the boxes, so it makes me slightly sad. But it does the trail. Okay? So it does just the trail. But do you guys get that just the trail still doesn't give you the big perspective? I like doing the full box to get the full perspective. Okay? Let's do another one. So 0, 0, negative 6. As soon as zeros show up in a point, you guys life gets a little less complicated. Okay? So if I want to plot 0, 0, negative 6, any thoughts of what that might look like? Literally treat it like direction. So 0 units front back, 0 units left right left, 6 units down. So start at the origin, and all you go is 1, 2, 3, 4, 5, 6. Put a point. There's point B. We'll come back and describe their locations as after we do all the plotting. Okay, so that's B. Okay, C, 2, 3, 0. 2, 3, 0. So only 1 0 shows up here, but let's see what happens. So 2, 3, 0. So again, start counting from the origin. And what first thing I should do is do what? What's the first instruction? Go 2 units forward. So 2 units in the positive x-axis. 2 units this way. Okay. And then 3 units in the y direction. Okay. And then how about the z direction? Okay, go any up in the z direction, or are we done? I think we're kind of done our path. So there's C. 0 in the y, 0 in the z direction. So you can finish off the picture here, but it won't be a box. What would be finishing off the picture here? Technically a rectangle, a perspective rectangle that's going to look like a parallelogram, right? So if I go 2 units back and 3 units across, okay? So I want you to understand, well, we'll talk about what it means in a moment. Let's finish the picture. So part D, -1, -3, 4. Okay, so now some more negative fun is happening. So -1, -3, 4. So what should be my first, again, starting at the origin, my first place to go is back 1 unit. Okay, so back a unit. And then 3 units to the, as Beyonce would say.
So if there's a 0 in it, then it means that.
Just don't move. Yeah, good, yeah. It'll be on a plane.
So if it's a 0 in any of them at all, it just means.
If 1 0 shows up, it means the point's going to lie on a plane. Yeah, good call. Do you guys get that? Like, are you guys starting to get the feel for how to do these dashes? Like, try your best to keep them all the same size, and try to keep the gap in between them the same size too, so that you're keeping things in perspective, right? Okay. So there's my 1 unit back, 3 units to the left, and then to finish this pathway off, I need to go 4 units up. Okay. Get in the habit, guys, to, as soon as you end your path, to like label it, or if it's a vector, like draw an arrow to end there, just so that that's drawn, and now build the rectangular prism around it. Okay, so how do I build this? So it's going to be 1, 2, 3 units, and 1 unit. Everyone happy? There's the bottom of my box. So start at the origin and do 3 dashes to the left, and then if you do it correctly, you should have one little space for a diagonal dash to match up with the single diagonal dash on the other side.
So when I'm building it, I go to the middle term first, the middle number first, do that.
I would say fill in the bottom box first. Yeah. And then once you have the 4 corners of the bottom of the box, then you can do the rest of the heights. So I know that in this case, the back is going to match up with the height of D because it went backwards. So I know that this is the exact matchup. I should, like, normally when I draw this, I literally look over here to see where the dashes are to kind of match, to try and do a copy paste to try my best to keep things lined up. Okay, because do you guys get, this is what ends up happening, and please don't be the student that does this. It's like 1, 2, 3, 4 horizontal. What? Like, you know what I mean? Like you can't have wonky looking boxes, right? It's not, or else you've defeated the whole purpose of this, right? So I'm purposely going, okay, 1 dash went about that high, and then there's the 2nd dash, and there's my 3rd dash, and there's my 4th dash. Because now when I draw across, it should be parallel to this across horizontal. This should be horizontal. Okay, so I
3 across at the back. 1, 2, 3. Back of box done. Now I've got to do the front of the box. And so it's along the along the Z axis, I need to go 1, 2, 3, 4 dashes up. Match it up over here. 1, 2, 3, 4 dashes up. And then 3 across and 1 there. And now, again, I can see the back, like, you guys see the back left up octant. You basically, when you draw one of these boxes, you guys you're creating an octant. You're creating one of the 8 spaces that's created in free space. Question? For the bathroom? Yeah, go ahead. So that's me plotting those 4 points. Now let's go back and describe the location. So in the first and the last, you guys get the best way to describe the location to literally use the octant description. So point A is in the what octant? How would we describe the point A? It's in the what letter? Front, right, left, right, top, bottom, top octant. Okay. Any thoughts on how you could describe point B? Yeah, go for it. Can you even be more specific? No, not just even the plane. What do we call these lines again, guys? They're axes. Is that a Z-intercept?
Tis a wolf. It is one.
Tis?
Tis. Can we write that?
Tis a.
Tis a.
Point B, sorry.
I'm writing that on the test list.
Point B is a Z-intercept. Okay? That should not be so mind-boggling crazy, right? You're allowed to have x-intercepts and y-intercepts. Why not a z-intercept? Okay? Look at the way the coordinates were. Normally we're used to intercepts being one of the coordinates is 0 and the other one is a number. If you're in 3 space and you're an intercept, how many zeros are you going to see? If you're an x-intercept or a y-intercept or a z-intercept in 3 dimensions, how many zeros will there be in the point? To be an intercept, 2 of the 3 coordinates have to be zeros. Okay? If it was -6, 0, 0, it would be an x-intercept. If it was 0, -6, 0, it would be a y-intercept. 0, 0, -6 is a z-intercept. So wherever the number is, that's the intercept. Okay? All right, for C. So for point C, I want you to understand it's same with B. Those points are not in octants. They're on boundaries of octants. In B, we were on an axis. In C, we're not on an axis, but are we still on a boundary between octants? Aren't we right on the border of a top-bottom, right? We're of the top-bottom. Like if you went up, you would be in a different octant than if you go down right here. So it's like we're on the barrier. And we kind of mentioned this, like we didn't draw a box here. We just completed a rectangle. And so if a point lies only in 2 dimensions, it's on a plane. And normally we're used to just the one plane that we've been using all along, the XY plane. We haven't really called it that. We call it just the Cartesian plane. But you guys have to be a bit more specific in 3 space. The XY plane is where point C lies. But if 1, 0 is in a point, do you guys get, you could be on a different plane. Okay? You could be on the XZ plane or the YZ plane. Okay? So you can live on a plane and not live in an octant in 3 dimensions. So point C is on the XY plane. That's how we write it. We do a double letter XY dash plane. Okay? And the clue is to look for 1, 0 in a point in 3 dimensions.
If there's 1, 0, you lie on a plane. Yeah, run. Okay. And then the last point, do you guys get the last point? It's going to look very similar like the first one. It's going to be an octant description. So point D is in the, so how would you describe this octant? Front, back. Which word? Front, back. This is a back, right, left, left, top, bottom. I'm going to make you hungry. We're in the BLT octant. You can let us know. Have you guys seen the RBC commercial lately about club sandwich?
Yeah, chicken lettuce. I know.
I had no idea either. You know that club sandwich is chicken lettuce under bacon.
Oh my god.
That's what club, when you see club sandwich, that's an acronym. It's not like, I thought it was like, ooh, I'm at the club sandwich. But it's CLUB, chicken lettuce under bacon. Things you learn.
I'm so shocked right now.
Yeah, it was like, who's that guy, Jay Barrett, like the guy who's in How to Train Your Dragon, he's on those RBC commercials now. Anyway, that was a real sidebar there, but that's okay. So that's how we draw points. Okay, do you guys think it's going to be a huge leap to draw a vector in 3 space? You literally just, but don't be the one student that does this. They do everything and then they just forget to draw the arrow. You guys, that's the only thing that's missing. You draw an arrow from origin to endpoint. Ta-da, now you've drawn a vector in 3 space. Okay, that's literally the only difference. That's why we spent so much time plotting points just now. Because if you can plot a point, you can plot a vector. You just join it to the origin. Okay? So now we know how to plot points in 3 dimensions. We're now going to look at how to graph 3D Cartesian vectors. So again, you're going to create, I'm going to tell you right now, any vector I make you draw will be a position vector. So I'm not going to be like, haha, start over here now and do one. I'm not going to do that to you, okay? But essentially you find your, if your tail's at the origin and the tip or head is at some point x1, y1, z1, then you just draw the point that's the end point and then draw your arrow from origin to there, okay? And again, do you guys see, hopefully you're going to kind of see how we're going to, everything we just learned about Cartesian vectors in 2 space is going to come into play with 3 space. Do you guys see there's an x component, a y component, and a z component? Okay, so just like we were adding vectors, we could add vectors with 2 dimensions, we could do it with 3, just add an extra dimension, but it's going to be the exact same rules. It's not like we throw in a whole bunch of different rules. Okay, so and again, just like we were just saying, so we had the building blocks of unit vectors I and j. Okay, so we want to have another unit vector that goes in the same direction as the z-axis. So ij, k. Okay, just kidding. No, not kidding. Okay, so we include k. So ijk is our combo for unit vectors that go in the x, y, and z direction. So vector k shows up. Okay, and so if I want to write my unit vectors, again, notice, as soon as I'm in 3 dimensions, you guys start getting used to this. This is the one big like brain adjustment. Three coordinate, triple coordinates. Okay, so the unit vector I still call it vector I, but you see in 3 dimensions, 1, 0, 0. I need an extra 0 to say don't go any in the k direction, or don't go any in the z direction. Okay, so I have 1, 0, 0. If you're on the y-axis, 0, 1, 0. And now here's my k vector, that's 0, 0, 1, that goes in the direction of the z-axis. And as with 2D directions, you can write a vector ABC in terms of its unit vectors. So, any thoughts? It'll be A times vector I plus B times vector J plus C times vector K. Again, what I'm trying to get at here is I can create 3-dimensional vectors, okay, by adding scalar multiples of unit vectors that go in the x, y, and z direction. I can build any vector in 3 dimensions by breaking it down to a front back coordinate, a right-left coordinate, and a top-bottom coordinate. If I take those three pieces and make an endpoint, I can draw any vector I like in 3 dimensions. Okay? All right. So how are we going to find the magnitude? Because I like to be able to find the length of a vector in 3 dimensions as well. So I could go through the reasoning why, and maybe I'll just do it, don't draw this, but I want you to understand the big picture here. I'm going to go back to I'm going to go back to this picture here, just as a reference. So if I want to find the length of this blue vector here, okay? I have 3, do you guys agree that it's not, if I travel along all 3 vectors, that's not a right angle triangle, there's an extra length, okay? But if I go part way, if I go 2/3 of the way, if I go along here and along here, is this a right triangle that I'm just drawing that's still living on the XY plane? This green vector that I just drew. Have I just created a green right triangle down here? Agreed? Yes? It's a right triangle. Remember, the big thing about perspective drawing here, guys, x-axis and y-axis, even though it doesn't look like it, it's a right angle, perspective drawing, right? Everything, all the axes intersect at right angles. So parallel to y-axis, and x-axis, this is a right angle right here. So take a look at this green vector. If I know that distance is to x1 and this distance is to y1, won't this be the square root of x1 squared plus y1 squared? Won't that be the magnitude of that vector? The length of the green vector there, okay? If that's the length of that vector, and then you have an extra vector, is there another right triangle that's like popping vertically up, where this is the right angle, where green is the bottom side, and I'm going to color in purple. This is your top side. Do you see there's another right triangle? And if I did put that, and if the blue vector here is the green magnitude squared plus purple magnitude squared, and then square root it, do you kind of see we're going to get x1 squared plus y1 squared plus z1 squared? Have I lost you? I feel like I lost you. Okay. So, okay. Does everyone buy into the green triangle? Let me draw it over here. Green triangle. I'm going to forget about vectors. All I'm going to say is this is x1 units long. This is y1 units long. If I do Pythagorean theorem, won't this side be the square root of those two sides? Is everyone happy that that's the hypotenuse of the bottom triangle? Okay, the green triangle. So that is the length. So now, this side, the hypotenuse of this triangle now becomes a leg of a different right triangle. So now I have a separate right triangle that kind of has this kind of format where I have, maybe this will help. This green side here is the same as that green side. So we have a square root of x1 squared plus y1 squared. So that's that length. The height, you guys see the height is z1. That's how high that piece is, z1. So this is a z1. Can I find this length? There's a right angle because, again, this is on a plane and this is vertical to the plane, so there's a right angle there. If I said do Pythagorean theorem again, okay, it's going to look a little silly, but this is what you're essentially doing. Okay, so I'm going to take this side and square it, and z1 and square it. What happens if you square a square root? You square a square root, cancel out, right? Do we all agree you would get x1 squared plus y1 squared plus z1 squared? Does that kind of look like an adjusted Pythagorean theorem? So this is an adjusted Pythagorean theorem for 3 dimensions. You just include the z direction too. So if you wrote that down, that's great. If you didn't, it's not a big deal because it's just, again, a formula that if I want to find the magnitude of a vector in 3 dimensions, I just have to square each dimension and then add them and then square root the result, and that will give me the magnitude of that vector. It's a way of finding lengths of vectors in 3 dimensions. Okay? Okay. So we're going to finish A and B today, and then we're going to call it a day, and then we'll finish this session. So for each of these 2 vectors here, we're going to sketch the vector, write the vector in terms of unit vectors, and find the magnitude. This is a very typical knowledge type question, right? Draw me the vector, tell me what it is as a sum and difference of vectors, and state the magnitude. So here we go. So it's exactly how we were plotting points, just draw the arrow. Don't forget the arrow. That's the important thing. Because if you do all the hard work and you don't draw the arrow, I can't give you full marks because you didn't actually draw the vector. So for 3, -1, 2. So let's do the building blocks there. 3, -1, 2. So I start at the origin and give me some direction. So I should start going 3 units forward. So 3 units in this direction. 1, 2, 3. 1 unit to the, and then how many units up? 2 units up. Okay, 1, 2. So instead of just putting a giant point there, right away I'm going to go, okay, origin to there, arrow. I have just drawn the vector u. Okay? Now, you guys get that if you don't complete the box, it's going to be hard to really visualize this in 3 dimensions. So let's complete the box. So let's finish the bottom of the box. So again, going along, it looks like it's going along vector u. You guys get that's a lie. Okay? You're extending horizontally. Okay, 1 unit. And then to meet up to down here, I need to go 3 in this direction. 1, 2, 3. There's the bottom of my box. How far up should each corner go, guys? I made these too thick. Too late now. So to go up, 1, 2. Up, 1, 2. Up, 1, 2. Okay, so here's my almost my full box done. I just have to finish up the top. So I have top, 3 dashes this way, 1, 2, 3, 3 dashes this way, 1, 2, 3, 1 dash that way. By completing the box, do you have the better feel of the 3 dimensions? Can you see, like, if you do this correctly, your arrow should start in one corner of the box and cross to a completely opposite corner of the box. As long as your vector does that, it means you've done it correctly. I'm in my vector in the box here starts at the back right down, and I end up at like front left top, and that's a good clue that I did it correctly. Without the box, though, it looks almost like the vector's horizontal, but you see it's not really. It's in 3 dimensions. It's still going upwards through the box. Okay. Okay, so now I've stated that. Let's write vector u in terms of its unit vectors. So this should be a free mark. All I want you to do is state that vector in terms of i's, j's, and k's. So the sum of vector, a scalar multiple of I, scalar multiple of j, scalar multiple of k, a sum of those. So what's going to be the coefficient of the I? It's going to be 3 vector I. What's going to come next, guys? Minus vector j plus 2 times vector k. Make sure your vector symbols are not on top of the numbers, just the vectors. So that's the key. Okay? And then we want the magnitude of this vector. So the magnitude of vector u.
So now you know the rule. You just have to go first coordinate squared plus second coordinate squared plus third coordinate squared. Find the answer. In this case, square root of 14. That's like a 4 or 5 mark question, perhaps.
If we did the calculation first, would it matter?
Nope.
Or it's just work better if you do the drawing?
You don't have to. The drawing is its own thing. You could do like I could ask you this question, write it in this form, and write the magnitude without needing the picture. But if the picture's part of it, you gotta do it. Yep. Yep. Okay, let's do this one last one before time runs out. So right away, we talked. What did I do? Oh, 14. I forgot the one. Sorry. Thank you. Got all excited. Okay. Root 14. Okay. Vector v is negative 2, 0, 1. Okay, a 0 has shown up. What did we say 1, 0 indicates? The vector is going to lie on a plane. Okay, you know, there's snakes on a plane, there's a vector on a plane. Okay, so there's a vector on a plane, and so when we draw this, we're not going to be able to draw a box, we're just going to be able to draw a parallelogram or rectangle. Okay, so let's see what we got here. Let's still draw the endpoint of this vector. So the first direction is the first information is a negative 2. So that tells me starting at the origin, where should I go? Back 2, so it means follow the x direction backwards. So in our minds, we're going into the paper. Okay? Okay, visually, we're going in opposite direction of x, so that's negative x, so negative 2x. And then 0 in the y direction, and then 1 in the z direction. So my 1 should be going, which direction? 1 should go up. Good. Okay. So we draw our single tick going up, and we put, instead of putting a point there, I'm going to say there's the end point of my vector. So I draw a vector from origin to there, and that is my, let's do this. This is my vector v. Okay. And to finish off the rectangle, okay, 1 unit, 2 units. So do you guys see? It's an extension on a plane. Like, how would you describe that vector lies on the what plane? Vector v lies on the xz, right? It has an x coordinate, has a z coordinate. So it's a point, it would be a point on, like, the end point is on the xz plane, so the vector will lie on the xz plane. It's a 2-dimensional vector in a 3-dimensional world. That's what this is. So if you had to write vector v in terms of its unit vectors, okay, what would you write next? So is there a vector I component? And if yes, what would be the number we write? So how many vector i's? 2, but we want it to be negative because we want to go backwards. We don't want to go in the same direction as the x-axis. As I, we want to go negative vector I. So negative 2 vector I. What do you think we should do about vector j? Goodbye, you don't count, no j. Okay? But we need a k, how many k's? Plus 1k. And again, if you're ever in doubt, like think logically what this says. Start at the origin, go 2 unit vectors backwards, and go 1 unit vector up. Isn't that literally the pathway you created? So like you can follow you guys get by doing the dashes like this, and I'm hoping as you did all the dashes, hopefully you're copying me, and a single dash counts as a unit. This is the one thing I don't like, and the textbook does it, and even if I show you this decimal thing, it does it. It just does dash, 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 dash. You guys, that doesn't tell me anything. Just they're doing like a dotted line. If you literally make the dashes you're counting,
then it'll guarantee the right proportion. So that's why I'm saying do it like that. And if you do it like that, then this literally becomes a unit vector count, right? Go 2 unit vectors backwards, go 1 unit vector up, and it matches up with your definition. We got one quick thing, guys. Magnitude. -2 squared plus 0 squared plus 1 squared is the square root of 5. High five, everybody. So, your goal is to complete up to 7.3, guys. Yep. You don't have to write it, but usually the convention is you just follow the formula, and so I would still put it in this. Thanks for listening, guys. 2 more teaching days, and we're going to be done this course. 2 more to go. Okay? See you tomorrow.